So today we're going to talk about ways of describing curves and surfaces, which are kind of the geometric objects that multivariable calculus equips us to study, using a strategy that's called parametrization. In other words, we're going to be finding parametric equations that are capable of describing a curve in n-dimensional space, right? But for us, for the most part, we're going to be in two-dimensional space or three-dimensional space, as well as vector-valued functions that are capable of describing surfaces. And the prototypes of curves and surfaces that we have so far are lines and planes. So in our last class, we sort of talked about what are some various ways of finding equations for lines and planes. And one of those two was something we ended up finding parametric equations for. So just to refresh our memories for a moment, when we came up with a strategy to find an equation for a line in three-dimensional space, we ended up using this formulation that's called a parametric equation. And it's called a parametric equation because what it does is it goes about describing every single point on this line in terms of a single variable that we call t, and that variable is what we call the parameter associated with this parameterization. So it's like you give me one quantity, a single scalar quantity called t, and I, using this function, produce all three coordinates of a point that belongs to that line that we're trying to describe, right? So you give me a scalar input, and I give you a whole vector's worth of output. And that's why in our textbook, this is called an example of a vector-valued function, right? The output from the function r is a vector, even though the input was just a scalar. And it seems like it's enough to provide a single parameter t to describe every single point along this line. But when we went to find equations for planes, we couldn't quite do the same thing. We took a different approach yesterday for equations for planes. And the equations that we came up with for planes ended up being what we call scalar equations, right? I called this elsewhere a level surface equation or a level set equation because what it does is it tells me kind of implicitly what are the coordinates of all of the points that belong to this plane. And it's implicit because I'm giving an equation that the x, y, and z coordinates must all satisfy. So it doesn't explicitly give us the coordinates of any one of those points. It just says whatever those coordinates are, they have to satisfy this equation. So that's one of the drawbacks of this approach to plane equations is it's not a parametric description. It's an implicit description, right? In order to find an example of a point which lies on this plane, I have to supply a value for x and a value for y, for example, and then I could use that value of x and y to determine a value for z. But I can't determine a value for any one of these variables unless I specify values for both of the other ones. And that actually is going to be our foothold at the end of our class today into parameterizing surfaces. In order to parameterize a surface, and a plane is our prototypical example of a surface, it's not enough to supply one value of a parameter. We would have to supply two of them. Because intuitively speaking, a line or a curve is kind of a one-dimensional type of object, right? That we can always either go forward or backward along a line or a curve, that those are the only two options for directions to go. And so somehow it's a one-dimensional type object. Whereas a plane, if I'm standing on a plane, or a surface, if I'm standing on a surface inside of three dimensions, is kind of a two-dimensional object, right? I can go north or south, but I can also go east or west, and I can go anything in between. So I have kind of a two-dimensional space of choices for which direction that I can walk along a plane or along a surface. And so when we parameterize a plane or parameterize a surface, we're going to need to use a vector-valued function that takes two parameters as input instead of one parameter as input. So that's the whole philosophy behind why we like vector-valued functions, is that they give us this very explicit way to, using only a single variable in the case of a line or a curve, or two variable parameters in the case of a plane or a surface, to describe that whole curve or surface inside of however many dimensions that we happen to be resident in. So first we want to just do some activities that get us used to the whole idea of parameterization for curves. So we're going to start mostly with those curves being in 2 dimensions, but then also sort of ramp that up to 3 dimensions toward the end of that section. And then we'll take a shift to do some calculus. So we're finally going to do some stuff this semester that resembles calculus. We'll take derivatives of parameterized curves and study sort of what those derivatives can tell us about the curves themselves. We might do, when I say integrals here, what I probably mean is antiderivatives. So let me just make that edit in here. Antiderivatives of vector-valued functions. We're not going to do too much of that yet. We're certainly not going to get to integrals for a couple of weeks in our course yet. So we're really just going to kind of use it as a way to undo derivatives. And in that, we're going to, a lot of what we do in the calculus section today is going to feel like physics. So if you've been in a physics class, particularly like a mechanics class, one of the things that vector-valued functions are really good at doing is using that one parameter, t, as a time variable and then describing the position, the location of something, a particle, a car, a person, within space or within the plane as a function of time, right? Because we can describe the x-coordinate, the y-coordinate, and the z-coordinate as all functions of that t variable. And so often we think of vector-valued functions or parameterized curves as kind of describing motion. There's a dynamic aspect to it. And so if we take derivatives of them, we're sort of describing how that location is changing as a function of time. And so it's going to give us an idea of a velocity, right? Which is any time that we talk about the time rate of change of a position, we're talking about a velocity. And the derivative of that, the second derivative of the position, would resemble something like an acceleration. So there's going to be sort of a physics, mechanics flavor to the way that we talk about parameterized curves when we do calculus with them. And then hopefully by the end of our time together today, we'll have had a little exposure to parameterized surfaces as well, where instead of one parameter t, we'll have 2 parameters t and s, and it'll give us the ability to go in sort of 2 independent directions along our surface. And for those of you taking linear algebra with me this summer, that notion of independence is something we're going to codify in linear algebra as linear independence. We want our 2 directions that we can go along a surface or a plane to not be overlapping with one another, to not describe the same direction. We want them to describe independent directions. We want each one of them to take us in a direction that the other one cannot. And so in linear algebra, we call that linear independence. So having 2 linearly independent directions that we can walk along our surface is why we have 2 parameters, one for each of those independent directions when we parameterize a surface. So that's kind of a long rambling agenda for what I hope that we'll accomplish today.